the number of ions, the degree of dissociation increases, hence the number of ions which is available for conductivity is also increasing. Lambda naught m is the limiting molar conductivity. A and root C. A is a constant and root C. What is the C here? It is the concentration. NH4Cl, which are the ions? NH4 plus and Cl minus. Na plus and OH minus in case of NaOH, and in the case of NaCl it is Na plus and Cl minus. So these two are added and the last one is subtracted. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry, Vidhyaashram School of Excellence, Mysore. So today we are back with session 6 of the chapter Electrochemistry. So in the last session, we studied about the conductivity of solutions, right? In today's session, we are going to study in further about the conductivity, that is molar conductivity. What is molar conductivity? The equations for it, how the molar conductivity will vary for a strong electrolyte, for a weak electrolyte and all of that, right? And then we'll study one of the important law which is KOHLRAUSC'S law, which is also important for your numericals as well, right? So let us begin with the first one, that is molar conductivity. So we already studied about conductivity, right? We studied resistance, resistivity, conductance, conductivity. Now what is molar conductivity? You are already familiar with the word mole and molar, right? So what is molar conductivity then? Molar conductivity is defined as the conducting power of all ions produced by the dissociation of 1 mole of an electrolyte dissolved in a given volume of the solution. So it is basically the conductivity of a solution which is having 1 molar concentration, or it is having 1 mole of an electrolyte. Okay, so the concentration will be 1 molar, or else it is the conducting power of all the ions which is produced by dissociation of 1 mole of electrolyte. Okay, so it is represented by the symbol lambda m. Okay, lambda and in the subscript m for molar conductivity. Right, it is related to the conductivity of the solution by the equation. So this is the equation, lambda m is equal to K by C. Okay, so now what was K? K is conductivity, right? So it is the conductivity of 1 mole of an electrolyte, right? It is the conductivity of 1 mole of an electrolyte. That is why K by C. Okay, so that C stands for the concentration. Okay, and we also know that the concentration is inversely proportional to the volume. So I can also write the equation as K into V. K by C or K into V. So this is the equation for molar conductivity. So I hope you understood what is molar conductivity. Conductivity of 1 mole of an electrolyte is called as molar conductivity. Right. So in the above equation, if K, what is K? Again, conductivity is expressed in Siemens per meter and the concentration is expressed in moles per meter cube, then the unit of molar conductivity are in Simon meter square per mole. Then which equation you have to use? It is this equation, that is lambda m is equal to K by 1000 into C. Right, K by 1000 into C, if these are the units for each of the quantities. If K is expressed in Simon meter and the concentration in mole per meter cube. Okay, so this equation you have to use where K is conductivity and C is the concentration. Now if we use Simon centimeter inverse, okay, the unit of K is Simon centimeter inverse and mole per centimeter cube is the unit for concentration, then we use this equation, that is lambda m is equal to 1000 into K by C. Okay, 1000 into K by C. Here the 1000 is in the denominator, here the 1000 is in the numerator. So these two equations are important for calculating the molar conductivity. I hope it is clear. Now, the variation of conductivity and molar conductivity with concentration. So when the concentration increases or the concentration decreases, we can also tell it in the terms of dilution. Okay, so dilution increases means what? I am diluting the electrolyte. Okay, diluting means more amount of water is added. So dilution increases means what is happening to the concentration? Yes, concentration is decreasing, right? Concentration is decreasing. Same way, when dilution decreases means what? Yes, the concentration is increasing, right? Yes, so I hope this relation is clear for you, right? So the conductivity, okay, not molar conductivity, just the normal conductivity always decreases with decrease in concentration, both for weak and strong electrolyte. So first of all, what is weak and strong electrolyte? Strong electrolytes are those electrolytes which completely dissociates into its ions. And weak electrolytes do not completely dissociate into its ions. Okay. For an example, for weak electrolyte is CH3COOH. Okay. CH3COOH. Right. So what happens to this? When it dissociates, you get CH3COO minus and H plus. An example for strong electrolyte is KCl. What happens? It dissociates into K plus and Cl minus. So strong electrolytes completely dissociate into its ions and weak electrolytes do not completely dissociate into its ions. Okay. So conductivity, when the concentration is decreased, always the conductivity also decreases. For even if it is for weak or strong electrolyte, in both cases, when concentration decreases, conductivity also decreases. Now coming on to molar conductivity. Now molar conductivity increases with decrease in concentration. Okay, molar conductivity increases with decrease in concentration. So can I also say that molar conductivity increases with increase in dilution? Decrease in concentration means increase in dilution, right? We have already studied this relation, just now I told you, okay? So molar conductivity increases with increase in dilution. This is because the total volume of the solution containing 1 mole of electrolyte also increases, right? We are increasing the dilution means the volume is also increasing, right? So that means molar conductivity increases with increase in dilution or decrease in concentration. Now let us see how molar conductivity is varying in the case of a weak electrolyte and strong electrolyte, and what is the reason behind it and what is the graph, all that we will study now. Okay, so first let us begin with the molar conductivity, the variation in molar conductivity for a weak electrolyte. Okay, so what was weak electrolyte? Which do not dissociate completely into its ions, right? Okay, so the degree of dissociation of weak electrolyte increases upon dilution. Okay, dilution means more amount of the solvent is being added. So what happens? Now the electrolyte is more diluted. Okay, hence the number of ions in the solution increases. More number of ions will be present now. Why? Because the degree of dissociation increases. As I told you, weak electrolytes is not having good dissociation. Now once it undergoes dilution, more number of ions will be present now because more dissociation will happen. Right. Thus molar conductivity gradually increases on dilution. Okay. So for weak electrolyte, what is happening? On dilution, the number of ions, the degree of dissociation increases. Hence the number of ions which is available for conductivity is also increasing. So what happens? Molar conductivity increases. So as you can see in this graph, okay, in this way, from left to right, the concentration is increasing. What we are talking about? Increase in dilution. That means concentration is decreasing. So from this direction to this direction, if I am moving, the concentration is decreasing, right? So as the concentration is decreasing or else the dilution is increasing, what happens? Gradually, you can see for weak electrolyte, yes, what is happening? The molar conductivity is increasing. This particular graph you can see is for weak electrolyte. Gradually it will increase, right, for weak electrolyte. Now, strong electrolyte is completely ionized in concentrated solution. Okay, the ions exist as ion pairs and it is not available for conduction. Okay, so that means let's take the example of KCl. So which are the ions? It dissociates into K plus and Cl minus. Now these ions in the solution, they will exist as pairs. Okay, if they are existing as pairs, are they available for conduction? No, they won't be available for conduction. So what happens when the dilution is increased? Now, if it is diluted again, now this pairs will break, and what happens? More number of ions will be available for conductivity. So, upon dilution, number of free ions increases. Okay, so upon dilution, what happens? This ion pairs will break, and the ions, the K plus and Cl minus, will be available for conduction, right? And the velocity of ions also increases, thus molar conductivity increases on dilution. Okay, so for weak electrolyte, what is the reason with which this molar conductivity is increasing? On dilution, the molar conductivity increases due to increasing number of ions, right? More dissociation will take place. In the case of strong electrolyte, on dilution, molar conductivity increases due to the increase in number of ions as well as the speed of ions. Yes, the velocity of ions also increases, right? So, increase in molar conductivity due to dilution for strong electrolyte is due to increase in speed of ions, right? And in case of weak electrolyte, it's due to increase in number of ions and the speed of ions. So, I hope it is clear. Now, let's see the graph for KCl as well. That's a strong electrolyte. As you can see, it is not having a steep increase as that of weak electrolyte, right? Weak electrolyte, two factors are contributing. One is number of ions and one is speed of ions, right? So, in this case, what happens? Gradually, it will increase, right? So, now one more thing you have to observe here is, in the case of weak electrolyte, as you can see, it keeps on increasing. It doesn't come and touch with the y-axis. That means the concentration is not touching to 0. It never becomes 0, right? As you can see, it can't be touched into the y-axis. But in this case, what happens? The KCl graph, if you are drawing, it finally touches at this point. Okay. So, now that point wherein which the concentration is 0, right? The concentration, it keeps on decreasing. Finally, it comes to 0. And the corresponding molar conductivity when the concentration is 0 is called as limiting molar conductivity. So, that is the next part that we are going to study. So, when concentration approaches to 0, the molar conductivity is known as limiting molar conductivity, which is represented by lambda naught m. Okay, lambda naught m, limiting molar conductivity. So, as you can see, for a strong electrolyte, if we draw the graph, finally it will touch this point where the concentration is 0. At that point, what is the molar conductivity? That is called as the limiting molar conductivity. And in the case of weak electrolyte, as you can see, it is not touching with the y-axis. Okay, so for strong electrolytes, the molar conductivity increases with dilution, we already studied, and can be represented by the equation. So, this is the equation which is relating molar conductivity and limiting molar conductivity. That is, lambda m is equal to lambda naught m minus a root c. Okay, lambda m is equal to lambda naught m minus a root c. Okay, so lambda m is the molar conductivity. Lambda naught m is the limiting molar conductivity. A and root c. A is a constant and root c. What is the c here? It is the concentration. Okay. So, the plot of lambda m, that is molar conductivity against concentration, root concentration, will be a straight line with intercept equal to lambda naught m. So, that means when a graph is plotted between lambda m and root c, lambda m and root c, we will obtain a straight line. As you can see, it is a straight line. The intercept, this part, the intercept will be lambda naught m, and the slope of this graph will be minus a. Right, the slope will be minus a and the intercept will be lambda naught m. That is the limiting molar conductivity. So, I hope you are clear with the equation as well. And what is limiting molar conductivity? It is the molar conductivity when the concentration is coming to 0. Okay. So, is that possible to calculate for weak electrolyte? No, right. It is possible to calculate for a strong electrolyte because it is touching here. Okay. For weak electrolyte, then how do we calculate it? Okay, for weak electrolyte, how do we calculate the limiting molar conductivity? So that also we are going to study here. Okay, now that is based on a law which is called as KOHLRAUSC'S law, which is a very important law. So let us understand what is a law. At infinite dilution, that means the dilution is maximum, okay, or the concentration is nearly equal to 0, right? So the electrostatic attraction between the ions is negligible. Okay, the dilution is maximum means the ions will be far apart. They won't be having any attraction with each other. Hence, each ions make its own contribution to the total conductance. Okay, so each ion will have its own concentration towards the conductance. Now what happens? It is infinite dilution means the dilution is to the maximum. So each of the ions is far apart, none of them is having an attraction with each other. So each of these ions is available for conduction. Each of them can conduct. Right. So now what happens is each of these ions will contribute to the conductance, total conductance, right? So the law states that at infinite dilution, limiting molar conductivity of an electrolyte can be expressed as the sum of molar ionic conductivity of anion and cation of the electrolyte. Okay, so at infinite dilution, the limiting molar conductivity can be expressed as the sum of the molar ionic conductivity of each of the ions present in it, right? So that is KOHLRAUSC'S law. So for example, in general, if you are taking, if an electrolyte on dissociation gives V plus, which is the cation, and V minus is the anion, then its limiting molar conductivity, lambda naught M, will be equal to, that is V plus, that is the cation, and its contribution, right? That is the molar ionic conductivity of cation plus molar ionic conductivity of anion. Okay, so this is called as the KOHLRAUSC'S law. That is, the limiting molar conductivity will be equal to the sum of the molar conductivity of cation, the contribution of cation, and the molar conductivity of anion. Okay, contribution of each ion, the molar conductivity of each ion is added. Together we will get the limiting molar conductivity. So this is called as KOHLRAUSC'S law. So for example, if we are taking HCl, HCl is dissociated into H plus and Cl minus, right? So if you have to find out the limiting molar conductivity of HCl, it will be equal to the molar conductivity of H plus the molar conductivity of Cl minus. Right, limiting molar conductivity of H plus and limiting molar conductivity of Cl minus. Same way, BaCl2. Now there is a 2 also. Okay, so it is dissociated into, barium chloride will be dissociated into Ba2 plus and 2Cl minus. Right. So how do I write the KOHLRAUSC'S law then? It will be limiting molar conductivity of Ba2 plus 2 into limiting molar conductivity of Cl minus. So this way you have to do the calculation. So I hope it is clear. Now weak electrolytes have lower degree of dissociation at higher concentration. Hence for such electrolytes, the change in limiting molar conductivity with dilution is due to the increase in dissociation. It is due to the increase in degree of dissociation. Right. So near lower concentration, lambda naught M increases steeply on dilution. So we already saw this. For weak electrolyte, the lambda naught M is steeply increasing towards the lower concentrations. So what happens? For weak electrolyte, it can be determined using KOHLRAUSC'S law. Using KOHLRAUSC'S law, we can determine the limiting molar conductivity. So let's see how we can determine it. For strong electrolytes, we can determine it because the concentration comes to 0. We can calculate the value. For weak electrolytes, how do we calculate it? We calculate it using the limiting molar conductivity value of strong electrolytes. So let's see. For example, the limiting molar conductivity of ammonium hydroxide can be calculated from the limiting molar conductivity of strong electrolytes, that is ammonium chloride, sodium hydroxide and sodium chloride. So I have to calculate the limiting molar conductivity of ammonium hydroxide, which is a weak electrolyte. So this can be done using the limiting molar conductivity of 3 strong electrolytes. So let's see how it is done. So the limiting molar conductivity of NH4Cl using KOHLRAUSC'S law, how do we calculate it? It will be the limiting molar conductivity of NH4 plus and Cl minus. Right. Now the same way for sodium hydroxide, it will be Na plus and OH minus. Limiting molar conductivity of Na plus and OH minus. Now for NaCl, it will be limiting molar conductivity of Na plus and Cl minus. So this three, using KOHLRAUSC'S law, we can find it. Now what is it that we have to calculate? It is that of ammonium hydroxide, NH4OH. So from these three, can you say we can add these three values? Okay, that is limiting molar conductivity of NH4Cl, NaOH and NaCl. If we use all these three values, we can calculate the limiting molar conductivity of the weak electrolyte. So that means limiting molar conductivity of NH4OH. Let's see. NH4OH dissociates into, that will be the sum of NH4 plus and OH minus. So as you can see here, NH4 plus is available here, OH minus is available here. Okay, so what do I do now is I add the limiting molar conductivity value of ammonium chloride and sodium hydroxide. Okay, so I will obtain these two values. Now, if I subtract the limiting molar conductivity of sodium chloride from that, okay, why I am subtracting limiting molar conductivity of sodium chloride? So this all will be removed then. So then what is the only limiting molar conductivities you have? That is will be NH4 plus and OH minus. So again let's see. The limiting molar conductivity of ammonium hydroxide will be equal to that of NH4Cl, NaOH minus NaCl. So let's see here. NH4Cl, which are the ions? NH4 plus and Cl minus. Na plus and OH minus in case of NaOH, and in the case of NaCl it is Na plus and Cl minus. So these two are added and the last one is subtracted. So now what happens? NH4 plus Cl minus here, Na plus OH minus here, Na plus and Cl minus is subtracted. Now the Cl minus and Na plus is subtracted. Now what is remaining? Limiting molar conductivity of NH4 plus and limiting molar conductivity of OH minus, which will give us the limiting molar conductivity of the ammonium hydroxide. Okay, so that means, so what is the use of this KOHLRAUSC'S law? Using the limiting molar conductivity of the strong electrolytes, we can calculate the limiting molar conductivity of the weak electrolytes. So I hope this is clear for you. Okay, so why did we subtract this limiting molar conductivity of sodium chloride? So that we only obtain NH4 plus and OH minus. So I hope it is clear. Now moving on to the next part, that is degree of dissociation. So now what is degree of dissociation? Which is represented by the symbol alpha. Which is represented by the symbol alpha. So it is the ratio of molar conductivity at any specific concentration to the molar conductivity at infinite dilution. So, degree of dissociation is equal to molar conductivity at any concentration. Okay, let's imagine the concentration as C. At concentration C, the molar conductivity divided by the limiting molar conductivity. So, this is degree of dissociation. Okay, and you can also write it in the terms of Ka, which you have already studied in your class 11, that is C alpha square by 1 minus alpha. So if you substitute the alpha value as lambda m by lambda naught m, you will get this, that is Ka. The acid strength will be equal to C lambda m square, that is the molar conductivity, divided by limiting molar conductivity into limiting molar conductivity minus the molar conductivity at concentration C. Okay, so that is Ka is equal to C lambda m square by lambda naught m into lambda naught m minus lambda m. So this is the equation for the acidic strength. Okay, Ka. Clear? So this is the degree of dissociation, this is the equation, and for Ka. So I hope it is clear. Now let's see the applications of KOHLRAUSC'S law as well. So using KOHLRAUSC'S law of independent migration of ions, it is possible to calculate limiting molar conductivity of any electrolyte solution from the individual ions, right? How do we calculate? For example, just now we discussed limiting molar conductivity of Ammonium chloride, if I have to calculate, it can be calculated by the sum of the individual ones, right? Individual ions. That is limiting molar conductivity of ammonium ion plus limiting molar conductivity of Cl minus, right? Also, for weak electrolyte, it is possible to determine the value from the strong electrolytes. Okay, lambda m, lambda naught m at C. Okay, at a given concentration C. So, using the limiting molar conductivity values of strong electrolytes, we can calculate it for weak electrolytes as well. So, I hope Kohlrausch'S law, the applications and how we can calculate for weak electrolytes using strong electrolytes is clear for you. So, in the next session, we are going to study about batteries, different types of batteries, primary and secondary batteries. And in that itself, we have to study few types of batteries. And the last one is corrosion. Okay. So, by this, we'll come to an end to this chapter. So, I hope what and all we have discussed in this session is clear for you. So, that's all for today. Thank you.